Hi everybody. This lecture focuses on highlights of Chapter 9. Chapter 9 is entitled Chemical Quantities and Reactions. And us chemists, we like to call it stoichiometry. So the first part of this chapter, we're going to focus a little bit more on than the second half of the chapter, because the second half of the chapter has concepts that are more focused in Chem 121. So the first three sections we're going to summarize together. Okay. Mole ratio and related calculations. Now, when you have a balanced equation, the balanced equation has the coefficients, and the coefficients represent the moles of each reactant and each product. It's like your recipe. Your recipe that tells you how many eggs you need, how much flour, how much oil you need to make what? One cake, or whatever you're making. Chemical reaction, very similar, okay? Except you're usually not going to be eating the reactants, okay? So you have your reactants, and you have the balanced equation. You have the coefficients from the balanced equation. You have your reactants, yield, your product, okay, your end result. So let's look at a balanced equation. Let's look at a synthesis reaction. If we take aluminum metal and over time it oxidizes, we get aluminum oxide, which doesn't happen too quickly because aluminum stays shinier a lot longer than other metals. Okay, if we balance this equation, we have two aluminums here, one aluminum there. Put a 2, okay, that would balance the aluminum. And then over here we have 2 oxygens and we have 3 oxygens. 3 times 2 is 6. So we need to make 3 here, 3 times 2 is 6, and 2 here, 3 times 2 is 6. But in that process we upset the balance of aluminum, so we need to change that coefficient to a 4. 4 aluminum, 6 oxygen, 6 oxygen. Now what these coefficients in the balanced equation tell us is that if we have 4 moles of aluminum metal reacting with 3 moles of oxygen gas, we will produce 2 moles of the aluminum oxide. Okay. 4 moles, 3 moles plus 2 moles. So if I say to you, if I have 4 moles of aluminum, how many moles of aluminum oxide will I produce? If I have 4 moles, I'm going to have 2 moles of this product as a result. Just like if I tell you I have 3 eggs, how many cakes can I make with 3 eggs? 1 cake, okay, if that's what my recipe is. Okay, so a mole ratio relates the quantities of the reactants to the products. So a mole ratio relates the mole quantities of reactants and products. Okay. We can also say 4 moles of aluminum will react with 3 moles of oxygen. We can have 4 to 3. We can have 4 to 2. Okay? So mole ratio relates the mole quantities of reactants and products. All right. Keeping that same equation, let's just write some mole ratios. Like I was just saying, let's actually write them out now. Okay, so I'm going to rewrite this same equation but a little bit higher on the board just so I have more space to work out below on my little tiny whiteboard here. I'm used to having several whiteboards and a smart board for space. And I've constricted to this. It's better than nothing, right? Okay. Mole ratios. Examples. 4 moles of aluminum will give 2 moles of aluminum oxide. That's one example. It's not the only example. 3 moles of oxygen will react to produce 2 moles of aluminum oxide. That's not the only example. We can say 2 moles of aluminum oxide are a result of 4 moles of aluminum reacting. And we can make a couple other combinations as well. 4 moles of aluminum will react with 3 moles of oxygen. Okay, these are examples of mole ratios from this particular balanced equation. Okay. So we know if we have 4 moles of aluminum reacting, that we're going to get 2 moles of aluminum oxide as a product. Well, what if we don't have 4 moles? How could we determine the quantity of the product that would result? We do a conversion problem, and we use the mole ratio as a conversion. So mole ratios are used as conversion factors to convert moles of a reactant or product to another reactant or product. Okay. So mole ratios are used as conversion factors to convert moles of a reactant or product to another reactant or product mole quantity. Right? So I'm going to still use this balanced equation up here. Okay? Using the balanced equation above, if 0.750 moles of aluminum react, how many moles of aluminum oxide form? Okay. Well, if we had 4 moles of aluminum react, we know we would get 2 moles of the aluminum oxide. But we don't have 4 moles. We have less, okay, which is realistic because you don't always have the exact mole quantities if you're doing a reaction. So then what we would need to do, we would need to use the mole ratio as a conversion factor. The mole ratio comes directly from the coefficients of the balanced equation. So in this case, we're comparing aluminum to aluminum oxide. So let's just write out 4 moles of aluminum oxide to 2 moles of, 4 moles of aluminum, I'm sorry, to 2 moles of aluminum oxide. Okay? Now, how we're going to put the given over the desired, we're going to do that in a minute. But we discerned that this is the information we need. We need that 4 and that 2. Okay? Now, our given quantity, we have 0.750 moles of aluminum. And we want to know how many moles of aluminum oxide form. So it's the same setup for any conversion factor, just like we learned in chapter 2. You have your given amount, and then you set your conversion factor up so that you have the desired unit on the top and the given unit on the bottom. Okay, and that comes from the equality that is relating the 2 units. So in this case, we want to convert into moles of aluminum oxide. So the mole ratio would have 2 moles of aluminum oxide over 4 moles of aluminum. Units of moles of aluminum cancel out, and then you do your math. You have 0.750 times 2 over 4, or you could do 0.75 times 1/2 if you wanted to reduce that. Again, depending how your comfort level is with the math. Okay, so 0.750 times 2, that answer divided by 4, or you could reduce that to 1/2, okay? Your final answer, regardless, should come out to 0.375 moles of aluminum oxide, okay? This is your final answer, okay? Okay, let's use the same balanced equation, but let's do a second example. And you know, you have your notebook out and you're copying it down just like we're in face-to-face lecture. You can always pause it and go back, all right? But it's good, I still stress to write it in your notebook because it helps. You're going to take courses beyond here, and you know, you have that notebook to go back to. All right. Writing helps it to sink in your head better. Writing or typing it, whatever. All right, let's do another example using the same balanced equation. Okay, if 0.850 moles of aluminum oxide are produced, how many moles of oxygen reacted? Okay, now we know how much product formed. We want to know how much reactant reacted. And stoichiometry problems are very realistic to anyone doing a reaction, whether it's a chemist or another scientist doing a reaction. If you need to know how much product you want to get, or how much of a reactant you have, or needs to be ordered, or will be put out by that, by that facility, this kind of calculation is done. Okay, using the mole ratio. There's other conversion factors that might be part of it as well, but this mole ratio is critical because it's relating one side of the equation to the other, one reactant to another product, or vice versa. All right, let's look at this problem. We're looking at these 2 substances, okay? Aluminum oxide and oxygen. Let's determine the mole ratio. 3 moles of oxygen will produce 2 moles of aluminum oxide. Okay, now how we're going to set them up depends upon our given over desired. We're starting off with 0.850 moles of aluminum oxide. And we need to set the mole ratio up so that the desired unit is on the top and the given unit's on the bottom. Okay? Well, 2 moles of aluminum oxide should be in the denominator, and the 3 moles of the oxygen should be in the numerator. Okay, so these units of moles of aluminum oxide cancel out. And then you would do your math. 0.850 times 3 divided by 2. Okay. You come out with 1.275. Okay, if we were picky with significant figures, 1.28 moles of oxygen. 3 significant figures in our initial measurement, 3 significant figures in our final answer. The mole ratio, okay, exact numbers. So just to emphasize again, this is the mole ratio. Comes directly from the coefficients of the balanced equation. Okay. So the problems that are assigned in the syllabus that go along with this are similar to this. Section 9.3 mentions the use of using molar mass as a conversion factor, and that's typically done in reality because you're not usually working with mole quantities. You're in a lab, you're in a in a plant, and you're not dealing with moles. You're dealing with grams or kilograms, okay, or some larger quantity. And molar mass is often used in the stoichiometry problems that would involve those units. We're not going to do that in Chem 110. Chem 121, that's very much part of that. But let me just write a statement about what I just said there. Okay. For example, if 0.750 grams of reactant react, how many grams of product will form? So in these calculations, 3 conversion factors would be utilized. Okay. You'd have your given mass quantity. Okay, your given grams, mass quantity. Your first conversion factor would be a molar mass. Your second conversion factor would be the mole ratio. And your third conversion factor would be the other molar mass to give you the desired mass quantity. Okay. And you can look in your textbook, section 9.3, and read that in further detail, especially those that plan to take Chem 121, okay? So if taking Chem 121, read section 9.3, okay? Because it's pretty much, in Chem 121, that's right where we start at, okay? All right, so we will not do problems with 3 conversion factors in Chem 110, just with the 1 conversion factor, which is the mole ratio, okay? All right, that concludes this lecture. The next lecture will be the remaining terms in chapter 9, okay?